Hello everyone. Today we are going to learn about an exciting aspect of modern computing, virtual machines. So, as we progress through our course, understanding virtual machines will be crucial as they play a significant role in how resources are managed and utilized in a variety of computing environments. So, virtual machines essentially allow us to run multiple operating systems on a single physical machine, each isolated from the others. During this lecture, we'll explore the architecture of virtual machines, including the types of VMs such as system virtual machines and process virtual machines. We'll discuss their roles, how they interact with the hardware and the host operating system, and the benefits they offer for system security and management. Okay, now let's take a look at the fundamental idea behind virtual machines. The core concept of a virtual machine is to abstract the hardware of a single computer into several different execution environments. This might sound complex, but think of it as dividing a single physical computer into multiple smaller virtual computers, each capable of running its own operating system independently. To understand this better, um, consider the layered approach that a VM has, like the host, virtual machine manager, or hypervisor, um, guest. These are the layered approach that VM uses. Okay, now if we look at the system models, so we'll examine the structural differences between non-virtual and virtual machines through system models. This comparison is crucial for understanding the operational differences and the efficiency that virtualization brings to system architecture. So, first of all, if you look at the non virtual machine model, here you see a straightforward model where processes interact directly with the kernel, which in turn communicates with the hardware. This traditional computing model is simple. There's a single operating system managing all hardware resources, and all processes run on this one OS. This setup is common in personal computers and systems where hardware abstraction is not required. In contrast, the virtual machine model introduces a layer called the virtual machine manager or hypervisor. This layer sits between the hardware and multiple guest kernels. Each kernel believes it has control of the entire system, but in reality, the hypervisor is managing the hardware resources and distributing them among multiple virtual machines, labeled here as VM1, VM2, and VM3. Now, each VM operates independently with its own OS, running processes as if on a dedicated hardware system. This is not only maximizes resource utilization but also enhances security and isolation between the processes running on different virtual machines. Okay, now here we'll see different types of hypervisors or virtual machine managers, which are essential for implementing virtual machines. The choice of a hypervisor affects the performance, scalability, and security of virtual machines. Let's explore the primary types. So first of all, the primary types, we have type 0. These are hardware based solutions directly controlling the best hardware and managing the guest um, VMs. The host hardware and managing the guest VM without the need for an underlying operating system. This type of hypervisor is embedded in the firmware of the system, offering high performance and security. So, for example, we have IBM, LPAR, and Oracle. Next, we have Type 1. So, it's known as bare metal hypervisors. These operate directly on top of the hardware. They offer robust performance and are typically used in enterprise environments. This category includes VMware, SX, Giant Smart OS, and Citrix Zen Server. Additionally, general purpose operating systems that provide standard functions as well as VMM functions, such as Microsoft Windows Server with Hyper V and Red Hat Linux with KVM, also fall under this type. Then we have Type 2. So, unlike Type 1, Type 2 hypervisors run on a standard operating system as applications. They are easier to manage and ideal for personal use or smaller businesses. Now, this type includes software like VMware, Workstation, and Fusion, um, Parallels Desktop, and Oracle VirtualBox. Now, which allow the host OS to manage the hardware and the hypervisor to provide virtualization services to guest operating systems. Next, we have some other variations which include para-virtualization. This is a virtualization technique where the guest operating system is modified to work in cooperation with the VMM. The goal here is to increase performance by reducing the amount of hardware emulation required. It involves an API for making system calls that the hypervisor handles rather than simulating hardware, which results in better performance and efficiency. Second, we have programming environment virtualization. This type of virtualization focuses on the creation of a virtualized environment specifically optimized for programming. Instead of virtualizing the whole system, this approach allows for the execution of applications within a managed code environment, like those provided by Oracle Java or Microsoft.NET. These environments help to manage code execution, memory, and other resources more efficiently than traditional operating systems. Now, third, we have emulators. Now, while not typically categorized strictly under virtual machines, but emulators play a crucial role in virtualization. They allow applications written for one type of hardware to run on a completely different hardware environment. For example, emulators make it possible for software designed for an Intel based Windows PC to run on an ARM based system. This is particularly useful in the development process and when transitioning applications to new hardware platforms. Okay, next we can say um, we have we now like turn to a somewhat different but related concept known as application containment. Unlike traditional hypervisor based virtualization, application containment does not emulate or virtualize hardware. Instead, it focuses on isolating applications within the operating system for enhanced security and manageability. Now, there are some key features of this, like first of all, segregation. Um, the primary purpose of application containment is to segregate applications from each other and from the core system. Um, This isolation helps in minimizing the potential impact of security breaches. If one application is compromised, the containment ensures that the breach doesn't spread to other parts of the system. So, for example, we have Oracle Solaris zones. Um, this allow for the creation of isolated, secured environments within a single instance of the Solaris operating system, where applications can run without affecting each other. Then we have BSD jails, like a similar technology available in BSD operating systems. Jails enable administrators to partition a BSD based system into several independent miniature systems called jails, each with its own space and resources. Then we have IBM AIX WPARs, which is workload partitions. Now, these are used to create virtualized operating system environments within a single instance of the AIX operating system, providing application isolation and resource control. Okay, now let's take a moment to reflect on the historical progression of virtualization technologies, which is crucial for understanding its significance and how far we have come. Now, first of all, virtualization first appeared in IBM mainframes in 1972. It was developed to allow multiple users to share a batch oriented system efficiently. This ability transformed how resources were allocated and utilized, marking the dawn of resource virtualization. Now, the formal definition of virtualization provided a framework that could be applied beyond IBM's proprietary systems, and described the three essential characteristics of virtualization. First is equivalence, like a virtual machine provides an environment for programs that is essentially identical to the original machine. Second is performance. Now, the program should run within this virtual machine, like the virtual environment, exhibit only minor performance decreases compared to running directly on the physical hardware. Third is resource management. Now, the virtual machine manager retains complete control of system resources, optimizing distribution according to need. Now, by late 1990s, advancements in Intel CPU technologies made it feasible to conduct research on virtualizing general purpose PCs, which previously lacked the necessary power of and efficiency. This period was crucial as it democratized access to virtualization technology beyond large scale systems to individual and commercial users. Then, like innovations by Zen and VMware, especially in the early 20s, revolutionized virtualization technologies. They developed solutions that are still heavily used today, paving the way for widespread adoption across different operating systems and hardware platforms. Today, virtualization has expanded immensely, encompassing not just mainframe computers but also many operating systems, CPUs, and virtual machine managers. This growth has enabled virtualization to become a backbone technology in cloud computing, enhancing scalability, security, and system efficiency across IT infrastructure. Okay, um, now let's see the benefits and features here. So first of all, if we talk about host and VM protection, Virtual machines provide an isolation layer between the host system and each VM. This isolation helps protect the host system from potential compromises within VMs, such as virus attacks. Similarly, VMs are protected from each other, which means that a virus or malware in one VM is less likely to spread to another. um, Second, we can say VMs can be frozen or suspended, allowing their state to be saved and then resumed at a later time. This is particularly useful for managing resources efficiently and quickly adapting to computing needs without losing data or state. It also supports taking snapshots, which are states of the system at a particular point in time. Now, these snapshots can be restored, allowing users to roll back to a previous state if needed. Additionally, VMs can be cloned, which means creating a copy of the VM that can run simultaneously, useful for testing, backup, or scaling purposes. Then we can say like flexibility and testing. Also, despite being isolated, VMs can share resources such as file systems and network connections, which facilitates complex setups for applications that need to communicate or share data securely. Now, virtual machines are invaluable tools for operating system research and software development. They allow researchers and developers to test a new operating systems, updates, and applications in a controlled and safe environments without affecting the main operating system. Now, um, now we can say one of the greatest advantages of virtual machines is their ability to run multiple operating systems on a single physical machine. This capability is crucial for application development, testing, and deployment, allowing developers to work in multiple environments without needing additional hardware. So, next we can say templating is a method to streamline the deployment of software and systems by creating a template of an operating system combined with specific applications. IT teams can quickly provision new virtual machines that are pre-configured with this setup. This is especially useful in environments where rapid scaling is necessary, such as in web hosting or enterprise applications. It ensures consistency across deployments and significantly reduces the time and effort needed to roll out new instances. Now, next we can say one of the most dynamic features of virtualization technology is live migration. Um, the process of moving a running VM from one physical host to another without interrupting service. This capability is critical for maintaining uptime duration maintenance or when balancing loads across servers to optimize performance. Live migration is a cornerstone feature that enables high availability and disaster recovery strategies, ensuring that services remain online even during hardware failures. Then, when we consider these features collectively, like templating, live migration, and the dynamic allocation of resources, they form the backbone of modern cloud computing infrastructures. Cloud services rely on these capabilities to offer flexible, scalable, and resilient computing environments. Through APIs, administrators and automated systems can manage vast arrays of hardware and virtual resources, deploying and scaling services as needed to meet the demand. Okay, now the core architectural components that make virtualization possible is so we'll learn about those things. Um, this is important because it lays the foundation for understanding how virtual machines operate at a technical level. Now, it's generally challenging to provide an exact duplicate of the underlying physical machine within a virtual environment. This is particularly true when the physical CPU supports only dual mode operation, which restricts the hypervisor's ability to fully manage the guest environments directly at the hardware level. However, as CPU architectures have evolved, so has support for virtual machine managers. Modern CPUs are designed with features that specifically support virtualization, such as Intel VTX and AMD V. So, these technologies provide better isolation, resource control, and performance for virtual machines, making it increasingly easier to emulate the full capabilities of the physical CPU within a virtual environment. Now, most virtual machines implement what is known as a virtual CPU or vCPU for each virtual machine. This vCPU represents the state of a CPU for the guest system as it believes it to be. When a VM is running, the VM manages the context switches between the physical CPU and the vCPUs of various VMs. This involves saving and restoring the state of the vCPU each time a switch occurs, um, ensuring that each VM believes it is operating independently on its own processor. Now, there are several techniques which are utilized to manage the efficiency and performance of vCPUs. These include, but not limited to, scheduling algorithms to optimize the execution time of various virtual machines, and um, so we'll see on the next slide here. Um, Dual mode CPU, which means guest executes in user mode. So, in traditional computing architectures, CPUs operate in two modes, user mode and kernel mode. User mode is where most of the guest applications run, and kernel mode is reserved for the operating system's core function. Now, in a virtual machine or virtual environment, it is imperative to maintain these modes distinctly for security and stability. However, it is not safe to allow the guest kernel to run directly in the physical CPU's kernel mode because it would have unrestricted access to hardware. Now, to address this, virtual machines implement two virtual modes, virtual user mode and virtual kernel mode. Now, on the virtual user mode, this is analogous to the user mode of the physical CPU where guest applications execute, and on the kernel mode is where the guest operating system kernel executes. Okay, now this mechanism is key to managing transitions between these modes, like trap and emulate mechanism. When a guest operating system attempts to perform an operation that would typically require kernel mode privileges, the CPU, under the direction of the hypervisor, traps this operation effectively. Um, the hypervisor then emulates the desired operation on behalf of the guest operating system This process involves the hypervisor determining the nature of the request, performing the operation securely, and returning the results to the guest operating system, all without ever granting direct kernel mode access. And when a guest operating system running in virtual user mode attempts to execute a privileged instruction, such as accessing hardware directly, this creates an error because such operations are restricted outside of kernel mode. This error triggers a trap. Then the virtual machine gains control once the trap is activated. It analyzes the cause of the error, emulates the intended operation securely within its controlled environment, and then returns control back to the guest system, all without ever allowing direct access to the hardware. Now, code running in user mode within the guest operates at the same speed as it would natively, because these operations do not generally require privileged access to the hardware. But when the guest needs to perform operations that would normally require kernel mode privileges, and the trap and emulate process can introduce latency. This is because every such operation needs to be intercepted, analyzed, and emulated by the VMM, which is more time consuming than executing natively in kernel mode. And this latency becomes especially significant in environments with multiple virtual machines. Like each VM requiring privileged operations must go through this emulation process, which can cumulatively lead to a decrease in overall system performance. Now, to mitigate these performance issues, modern CPUs are increasingly being equipped with hardwares um, hardware support features designed to optimize virtualization tasks. These enhancements help streamline the trap and emulate process by reducing the overhead associated with these operations, thus improving the performance of VMs running on such CPUs. Okay, let's see a diagram here where we have user processes. These are standard processes running within the guest operating system, operating primarily in user mode. When these processes attempt to execute a privileged instruction, something that typically requires kernel mode access, the guest OS cannot handle it directly due to the restrictions imposed by virtualization. The attempt to execute a privileged instruction triggers a trap. This is a critical point where the guest OS yields control to the VM, signaling an operation cannot be executed directly by the guest in its current mode. Upon receiving the trap, the VM takes over. It analyzes the attempt operation to determine exactly what the guest intended to do. Now, the VMM emulates the privileged instruction on behalf of the guest. This emulation is performed securely within the VMM's controlled environment, ensuring that the operation does not compromise the integrity of the host machine or other virtual machines. Once the emulation is complete, the VMM updates the virtual chip CPU state to reflect the outcome of the emulated instruction, maintaining the illusion for the guest operating system that it has executed a kernel mode operation. After the emulation and state update, control is returned to the guest operating system, allowing user processes to continue operation as if the privileged instruction was executed normally. Okay, so there's another crucial aspect of virtualization technology known as binary translation. This process is vital for dealing with CPUs that do not have a clear separation between privileged and non privileged instructions, which can significantly impact the efficiency and security of virtual machines. So, some of the early Intel 86 CPUs, which were initially designed for calculators and not for complex computing systems, do not have a clean separation between privileged and non privileged instructions. This lack of separation poses challenges for implementing secure and efficient virtualization. These CPUs must maintain backward compatibility which often complicates the introduction of enhancements aimed at better support for virtualization. Now, the pop F instruction is used to load the CPU flags register from the contents of the stack. This instruction's behavior changes based on the mode in which the CPU is operating. First of all, we have privileged mode. Like if executed in privileged mode, pop F replaces all flags in the flags register, allowing full control over the processor's state. And in user mode, pop F only modifies some of the flags, leaving others intact to prevent unauthorized changes to critical CPU settings. Crucially, executing pop F in user mode does not generate a trap, which means the hypervisor may not be aware of changes to the CPU state if it relies solely on traps to intercept sensitive instructions. Because some instructions like popf can operate under the radar of the typical trap and emulate mechanism, alternative strategies such as binary translation became necessary. Binary translation involves converting privileged instructions into a sequence of safe instructions that achieve the same end result but can be controlled and managed by the hypervisor. So, traditional trap and emulate strategies struggled to handle certain instructions efficiently, particularly those do not generate traps yet alter the state significantly. These are referred to as spatial instructions. For example, some instructions might change the state of the CPU silently without altering the hypervisor through a trap, making them difficult to manage in a virtualized environment. Binary translation emerged as a solution to these challenges around 1998 when it became feasible to translate problematic CPU instructions into safer hypervisor controlled operations. Now, while the basic idea is straightforward, translate one set of instructions into another. The actual implementation involves intricate programming and deep integration with the CPU architecture. So, when the guest's virtual CPU is in user mode, it executes most instructions natively without intervention, as these do not typically affect the system state outside of the guest's scope. When in kernel mode, the vCPU may believe it has full kernel privileges. Here, the VMM preemptively examines the instructions about to be executed to ensure that they do not compromise the host system or other VMs. These continue to run natively, like as they do not pose a risk to system integrity. Non-spatial instructions and spatial instructions are translated into a new set of instructions that perform an equivalent task but in a manner controlled and safe for the virtual environment. For instance, an instruction that directly manipulates hardware state is translated into a Benning equivalent that instead updates the state within the vCPU. So, this method ensures that all guessed operations, even those involving complex or non trappable instructions, are performed safely and predictably, maintaining the isolation necessary for secure and stable virtualization. It also allows the VMM to maintain a consistent view of the guest state, crucial for tasks like live migration and state snapshotting. Okay, if we talk about binary translation in virtualization, which involves dramatically reading the native instructions from the guest system, analyzing them on demand, and generating native binary code that the host machine can execute directly. This translated code replaces the original instruction sequence, ensuring that the guest system operates seamlessly without realizing that its instructions are being intercepted and modified. The translated instructions are executed in place of the original code, providing the guest with the illusion of executing on its native hardware. So, initially, one might expect that the performance of a system employing binary translation would be poor due to the overhead of intercepting, translating, and executing each instruction. However, significant optimizations have been developed to mitigate these performance penalties. Now, products like VMware employ sophisticated code caching mechanisms to enhance the efficiency of binary translation. Once a special instruction is translated, once it is stored in a cache. So when the same instruction sequence needs to be executed again, the VMM can directly retrieve the translated code from the cache instead of translating it again. Okay, to illustrate, consider an example where booting Windows XP as a guest involves approximately 950,000 translations. So each translation might add about 3 microseconds of delay. Despite these additional microseconds per instruction, the overall slowdown is only about 3 seconds or 5% compared to native execution. This relatively minor slowdown is a testament or to the effectiveness of caching and other optimizations in binary translation strategies. Now, this visual helps to conceptualize the complex interactions between the guest operating system, the virtual machine manager, and the virtual CPU. So, first of all, if we talk about the guest's user, so it processes may attempt to execute instructions that interact with the system at a deeper level. Typically reserved for the operating system, these instructions are termed special instructions because they require privileged access. Initially, the VMM reads the instructions that are executed by the guest. This step is crucial for identifying any special instructions that might affect the system state or security. Now, upon detecting a special instruction, the VMM translates this instruction into one or more secure operations that will have the intended effect without compromising the host system or other guests. This translation is performed in real time and is tailored to maintain the operational integrity and security of the overall system. After translation, the VMM executes the translated instructions on behalf of the guest. This ensures that all operations conform to the security and operational policies set by the VMM. Now, Um, like post execution, the VMM updates the vCPU's state to reflect the results of the executed translation. This update is crucial as it maintains the continuity and consistency of the guest's perceived environment, ensuring that the guest OS and its processes believe they are interacting directly with the hardware. Once the vCPU is updated, control is returned to the guest OS, allowing user processes to continue their operation under the illusion of an uninterrupted access to the system resources. Okay, now let's talk about nested page tables. It is also another important mechanism for handling memory management challenges in virtualization. This technology is essential for maintaining the performance and stability of virtual machines by managing the translation of virtual memory addresses to physical memory addresses. In a virtualized environment, both the guest and the hypervisor need to manage memory effectively. However, both entities need to believe they have control over the physical memory, which introduces complexity. How can the virtual machine manager maintain a consistent and accurate mapping of memory addresses that satisfies the requirements of multiple virtual machines? Now, each guest VM maintains its own page tables, which are used to map its virtual addresses to what it perceives as physical addresses. However, these physical addresses are actually virtualized addresses provided by the VMM. Now, the VMM uses nested page tables to manage these mappings at a meta level. NPTs track the mappings from the guest's virtual addresses to the actual physical addresses of the host machine. Just as a virtual CPU stores the state of a guest CPUs, the NPTs store and manage the state of a guest's memory table mappings. When a VM is running on the CPU, its NPTs are treated as the active system page tables. Now, if a guest attempts to modify its page table, the VMM intercepts this change. It then updates the NPTs to reflect these changes consistently across the system, ensuring that the physical memory's integrity and isolation are maintained. Now, managing these translations can be resource intensive. So, frequent updates to the page tables can lead to increased translation look aside buffer misses, which in turn can significantly slow down the performance due to the added overhead of refetching the address mappings. Okay, now here we'll see particularly how advancements in processor technology have significantly improved the performance, stability, and feature set of virtual machines. Um, so, in 2005 and 2006, Intel and AMD introduced hardware virtualization extensions, VTX and AMD-V, respectively. Now, these technologies were designed to overcome some of the limitations posed by earlier CPU designs that lacked specific support for virtualization. Now, these hardware enhancements have drastically reduced the need for binary translation by providing more direct support for virtualization tasks. They handle complex operations natively that previously required the VMM to use more resource intensive software methods. So, with VTX and AMD-V, CPUs can define multiple modes specifically tailored for virtualization, distinctly separating guest and host modes. Now, this separation allows for host mode like the VMM can operate with full control over the hardware configuring and managing guest VM. And on guest mode, here system operating systems run as if they are on native hardware, unaware of the virtualization layer. So these extensions allow guest systems to access virtualized hardware directly, such as network adapters or GPUs, while still maintaining overall system security. Privileged instructions from VMs cause traps to the VMM, ensuring that the VMM retains ultimate control over hardware interactions. So the CPU maintains a virtual CPU for each VM, handling context switches and state management, which are critical for maintaining performance and isolation between VMs. Now, hardware support has also expanded to include nested page tables, which improve memory management between host and guest systems, reducing the overhead for address translation. Um, like direct memory access DMA and improved interrupt handling mechanisms are also supported, um, enhancing the efficiency and responsiveness of virtualized environment. Okay, now here in this diagram it represents the nested page tables mechanism, which is instrumental in handling memory translation in virtualized systems. Now it breaks down the complex process into understandable components. So first of all, if we talk about guest virtual address, like this represents the virtual addresses as seen from within the guest operating system. The GVA consists of several components such as the PML4 directory, PTR directory, like table and offset, which are part of the 8664 paging structure. The address translation process involves several stages. So first of all, PML4E, which is the top level directory entry in the paging structure. Then PDPTE, which is this entry points to the page directory. PDE and PTE, these further refine the mapping, breaking down the virtual address into more manageable chunks, eventually pointing to the physical address. Okay, now the final target of the translation process, which is the actual physical address on the host machine where the guest's data resides. And the diagram shows how each layer of the guest's virtual address is mapped through the nested page tables system to resolve to the host's physical address. Each step down the translation hierarchy refines the address mapping further, ensuring precise control and isolation of memory resources across different virtual machines. NPTs provide an efficient way to manage the memory of multiple VMs on a single host, allowing each VM to operate as if it has its own physical hardware. And this mechanism also secures each VM's operations by isolating their memory spaces, preventing them from interfering each other. Okay, now here see types of virtual machines and implementations. First of all, if we say variations and hardware utilization, we have like virtual machines leverages hardware features to simplify and enhance the implementation of VMs. These features can significantly improve performance by allowing more direct access to physical resources, reducing overhead and optimizing operations. Now, depending on the virtualization approach, VMs can vary significantly in how they interact with hardware. For example, Type 0 hypervisor provide VMs with dedicated resources, potentially offering better performance when but at the cost of flexibility. So VMs VMs are created by a VMM, like virtual machine manager. So with specific resources assigned such as CPU cores, memory, networking and storage capacities. Now the allocation of these resources can be static or dynamic depending on the type of hypervisor and the specific requirements of the VM. In Type 0 hypervisors, resources are usually dedicated, while other types may allow for shared or mixed resource usage. This affects the VM's performance, scalability, and efficiency. When a VM is no longer needed, it can be easily deleted, so which frees up its assigned resources. Now, one of the significant challenges in virtualized environment is VM sprawl, where the rapid uh, proliferation of VMs leads to management difficulties. VM sprawl can result in underutilized resources, increased operational cost, and complexity in tracking and maintaining the state of and history of numerous VMs. Now, there are some effective lifecycle management, like clear policies on VM creation and deletion, and regular audits of VM usage and necessity are crucial strategies to combat VM sprawl. Okay, now we'll talk about an older yet significant classification in the realm of virtualization technologies. First of all, like these Type 0 hypervisors are implemented directly by firmware at the hardware level. Um, the operating systems running on Type 0 hypervisors require no special modifications to interact with the hypervisor since the VMM is integrated within the firmware. Each guest VM needs under a Type 0 hypervisor has dedicated hardware resources. Now, one of the significant challenges with Type 0 hypervisors is managing I/O resources, particularly when it is difficult to dedicate enough devices and controllers to each guest. This can lead to bottlenecks and reduced performance. To manage shared I/O and other resources, Type 0 hypervisors sometimes implement a control partition. This partition runs daemons or services that facilitate communication and resource management among various guest VM. Now, Type 0 hypervisors can support scenarios where a guest VM acts as VMM itself, hosting further guest VMs. This setup is known as virtualization within virtualization, adding another layer of complexity and potential for resource management. So, while theoretically feasible, nested virtualization is more complex to implement effectively on Type 0 hypervisors compared to newer types. Okay, now this is an example of is the diagram of the Type 0 hypervisor. Okay, now see the Type 1 hypervisors, which are integral to the operation of many contemporary data centers. Um, so we'll see some key features, benefits, and operational aspects of Type 1 hypervisors of enterprise virtualization strategies. So, unlike Type 2 hypervisors that run at an existing operating system. Type 1 hypervisors run directly on the host hardware. This characteristic allows them to provide better performance and more direct control over the hardware. They are specialized operating systems designed specifically for virtualization, managing operating system directly without the need for underlying host operating systems. So, in many ways, Type 1 hypervisors are becoming what might be termed data center operating systems. They allow data center managers to control and manage operating systems and applications in sophisticated ways that were not possible with traditional hardware setups. One of the primary benefits is the consolidation of multiple operating systems and applications onto fewer physical machines, optimizing hardware use and reducing costs. These hypervisors can move case systems between physical hosts to balance loads and optimize performance, an essential feature for maintaining high availability and efficiency in data centers. Type 1 hypervisors support taking snapshots of the entire state of a VM at any given point in time. These snapshots can be used for backups or for quickly cloning new VMs, like significantly speeding up deployment process. Because they interact directly with the hardware, Type 1 hypervisors implement device drivers for the host hardware, which other components cannot do. This setup ensures that all hardware operations are efficiently managed by the hypervisor. So, typically, guest operating systems do not know they are running within a VM. This transparency ensures that applications run on guest OS without modification for virtualization. And type 1 hypervisors run in kernel mode, giving them full control over the hardware, which is crucial for managing multiple VMs securely and efficiently. Okay, now we'll explore the variations within the Type 1 hypervisors, specifically those that integrate the functionalities of general purpose operating systems with virtual machine manager capabilities. So, this type of hypervisor is particularly significant in environments where flexibility and resource management are essential. So, unlike traditional Type 1 hypervisors that solely focus on virtualization, certain general purpose operating systems have been enhanced to perform dual roles. These systems manage regular OS tasks and also function as hypervisors, managing virtual machines directly. For example, KVM is a um, integrated into KVS is integrated into the Linux kernel, allowing RHEL to run VMs alongside regular Linux processes. Then Windows with Hyper-V. So Microsoft has integrated Hyper-V into its Windows Server and some desktop versions, enabling these systems to host VMs. Then we have Oracle Solaris, which is known for its robust scalability and security features. Oracle Solaris can also manage VMs directly through its built in virtualization capabilities. Then, these systems are typically less feature rich in virtualization specific functionalities compared to dedicated Type 1 hypervisors. However, they offer a significant advantage by seamlessly integrating virtualization into an environment that also supports standard OS operations. So, in these setups, VMs are treated much like any other process from the OS perspective, but with specialized handling for virtualization specific tasks, such as managing CPU scheduling, memory allocation, and I/O operation. So, when a guest operating system running under such a hypervisor tries to execute special instructions or accesses hardware directly, these requests are handled differently. The hypervisor component of the OS intercepts these calls and manages them to prevent direct hardware access, ensuring that the virtualization layer maintains control and security. So, by combining general OS functionalities with hypervisor capabilities, these systems simplify the architecture for users and administrators, providing a familiar environment for both managing applications and virtual machines. They allow for more dynamic resource management, as the hypervisor can allocate resources not only based on VM needs but also according to the requirements of the host operating system's process. Okay, now let's talk about type 2 hypervisor. Like this type of hypervisor offers unique benefits and some limitations in terms of performance and system integration. So, unlike Type 1 hypervisors that run directly on the hardware, Type 2 hypervisors operate as a software layer installed on top of an existing host operating system. This setup means that the hypervisor is essentially another application within the host operating system environment. So there is very little direct involvement or modification required from the host operating system to accommodate the hypervisor, making type 2 hypervisors particularly versatile and easy to deploy. So since type 2 hypervisors do not require changes to the host OS, they can be installed and used much like any other application. So, this is beneficial for users who need a simple setup to run multiple operating systems, such as students or developers who might need to operate Windows, Linux, and Mac OS on the same physical machine. So, they allow for the running of multiple guest operating systems concurrently, each within its own virtual machine. This flexibility makes Type 2 hypervisors popular in educational settings, software testing, and development environments where multiple operating systems are required for different tasks. So, we can say it generally exhibit poorer performance compared to Type 1 due to the additional overhead imposed by running on top of a host operating system. They cannot leverage certain hardware optimizations that are accessible to Type 1 hypervisors, which interact directly with the physical hardware. So the idea, like the ideal type 2 hypervisors are like where's ease of setup. It is better when we think about ease of setup, flexibility, and the ability to quickly switch between different operating systems. Um, and they provide an excellent platform for learning about different OS. Okay, now next think about like in para virtualization, the guest operating system are explicitly modified to work in a virtualized environment. This modification involves replacing non-virtualizable instructions with hypercalls, and that communicate directly with the hypervisor. So, because the guest OS is aware of being virtualized and can directly interact with the hypervisor, paravirtualization can significantly reduce the overhead associated with hardware emulation, leading to improved performance. Okay, now the VMM provides specific services that support the modified operations of the guest OS, and these modifications enable the guest to run more efficiently than in traditional virtualization scenarios. As hardware, so Zen is a notable leader in the paravirtualization space. It has developed several advanced techniques that enhance the operation of the virtual machine. And it provides clean and simple device abstractions that facilitate efficient I/O operations. Um, Now, the direct interaction between the guest OS and the hypervisor can significantly reduce the time spent in sensitive operations, and this is the advantage of paravirtualization. And also, by providing straightforward abstractions, paravirtualization simplifies the management um, of device interaction, which can otherwise be complex under full virtualization. Okay, now let's take a look at this diagram, which shows how the Zen hypervisor handles I/O operations using a shared circular buffer, a key component in its architecture for efficient communication between the guest operating system and the hypervisor. Now, the shared circular buffer in Zen is designed to facilitate smooth and efficient I/O operations between the guest OS and Zen. This buffer manages data transfer requests and responses in a streamlined manner, minimizing overhead and maximizing throughput. And this segment of the buffer holds like the request queue, which holds descriptors that are queued by the virtual machine but not yet processed by Zen. These descriptors contain details about the I/O operations requested by the guest OS. These are slots in the buffer awaiting for a response from Zen. Once Zen processes a request, the corresponding descriptor moves from the request queue to this part of the buffer, which is outstanding descriptors. Then, after Zen processes a request, the results are placed in the response queue. This part of the buffer holds descriptors that have been serviced and are ready to be returned to the guest OS. And then there are some unused descriptors, and which represent that the free slots in the buffer that are available for new requests or responses. So, basically, unlike some other virtualization approaches, Zen's paravirtualization does not use nested page tables for memory management. Instead, each guest has its own set of read-only tables. And when a change in the page table is required, the guest OS makes a hypercall to the hypervisor. This is a direct communication method that allows the hypervisor to manage memory more efficiently than standard hardware assisted techniques. So initially, paravirtualization was particularly valuable for virtualizing older 86 CPUs. that did not support hardware assisted virtualization. It enabled these CPUs to support virtualization by modifying the guest OS to run on a para virtualized VMM without the need for binary translation, reducing overhead and improving performance. As hardware evolved, newer CPUs included more robust support for virtualization and decreasing the necessity for extensive modification to the guest OS. So then Zen has adapted by reducing or eliminating the need for guests to be modified for para virtualization, which is to making it easier to manage and deploy VMs on modern hardware. Okay, now we can say that in programming programming environment virtualization, so this type of virtualization does not virtualize hardware directly but rather provides a consistent programming interface across various underlying systems, and the Java virtual machine is a prime example of this concept. So programming environment virtualization, PEV, is designed to run within a custom built environment that abstracts away the underlying hardware and system specifics. This allows developers to write code that runs consistently across different platforms. Now, Oracle's Java is a key example where the JVM provides a virtualized environment that allows Java applications to run uniformly on any system that has the JVM installed, regardless of the underlying hardware or operating system. Okay, now this one is an older yet significant method of running one operating system on a hardware platform. It was not originally designed for. So, unlike virtualization that often requires the same underlying CPU architecture, emulation allows for the operation of systems across different hardware architectures. Now, emulation involves creating a software based environment that mimics the hardware of one system on another. This allows software compiled for a particular CPU architecture to run on a completely different architecture. The core functionality of an emulator is to translate the guest system's instructions into the native instructions of the host CPU. This process is comprehensive and involves emulating not just the CPU but also the associated hardware like memory management units and I/O devices. It is generally slower than running applications natively because of the overhead involved in translating instructions from one architecture to another, and this can be an order of magnitude slower depending on the complexity of the emulation. Um, Unlike virtualization, which typically runs a guest OS on the same type of CPU as the host, emulation does not require similar underlying architecture. Okay, now this architecture diagram is essential for understanding the layers and components involved in VMware approach in virtualization. So, VMware Workstation operates as a Type 2 hypervisor, meaning it runs on top of a host operating system, unlike Type 1 hypervisors, which run directly on the hardware. And this setup allows VMware Workstation to leverage the existing drivers and management features of the host operating system. At the base, the host operating system, such as Linux, provides the primary interface with the hardware and manages physical resources. It supports the higher layers where virtualization occurs, and the hardware layer directly interacting with the OS, with the host OS. The hardware layer includes the CPU, memory, and I/O devices that are essential for both the host and virtual machines. Now, above the host OS sits the virtualization layer. This layer is responsible for creating and managing virtual machines. It abstracts the hardware resources from the host OS and allocates them to each VM as needed. Then each guest operating system has associated virtual hardware, including a virtual CPU, virtual memory, and virtual device. These components simulate the corresponding physical hardware, allowing guest operating systems like FreeBSD, Windows NT, and Windows XP to operate as if they were running on their own separate machines. Now, multiple guest operating systems can run concurrently, each in its isolated partition. These operating systems are obvious to the fact that they are not interacting with real hardware but with virtualized equivalents provided by VMware. So, each virtual machine is completely isolated from others, ensuring that processes in one VM do not interfere with the other one. So, we can say that by abstracting hardware into multiple virtual machines, VMware Workstation allows for flexibility, resource efficiency, and enhanced productivity for various use cases, from software development to educational environments. So that's all for our lecture, virtualization. I hope you understand about that. If you have any question, feel free to email me, and thank you all.